Welcome to Math, Week 10, Quadratic Functions and Vertex Form. This is Module Math 1 on the Math Tutor's Self-Study track. Today's lesson runs about 120 minutes with a 10-question practice quiz at the end. This week we shift from factoring to graphing. We will see the same quadratic written in three forms: standard, factored, and vertex. We will learn which form to reach for depending on the question being asked. We finish by linking parabola geometry to mean squared error loss surfaces in linear regression and to the Gaussian density. This video is sponsored by Subthesis. Visit subthesis.com to learn more. A quadratic function f of x equals ax squared plus bx plus c graphs as a parabola. Its shape and position are completely determined by a, b, and c. This week's job is to learn to read those parameters off any of three equivalent forms. Here is the agenda. We start with the three forms and what each one lets you read off easily. We use the leading coefficient a to predict opening direction and width. We find the vertex two ways, the formula x equals negative b over 2a and completing the square. We connect parabolas to mean squared error loss in machine learning and to the Gaussian density in probability. Then quiz, recap, and preview. A quadratic comes in three equivalent forms, and each makes a different feature obvious. Standard form ax squared plus bx plus c is what you usually start with. The y-intercept reads off as c directly because f of 0 equals c. Factored form a times x minus r times x minus s exposes the x-intercepts. The roots are r and s. Vertex form a times the quantity x minus h squared plus k exposes the vertex coordinates h, k. Each form is useful for a different question. To find the vertex, convert to vertex form. To find roots, convert to factored form. The skill this week is moving between them, especially completing the square to get from standard form to vertex form. Why do we need three different ways to write the same function? Because each form makes a different feature immediately visible. Standard form reveals the y-intercept at a glance. Factored form reveals the x-intercepts, the roots. Vertex form reveals the vertex, the turning point of the parabola. You choose the form that matches the question you are trying to answer. If someone asks, where does the graph cross the y-axis? Use standard form. If they ask, where is the maximum or minimum? Use vertex form. The quadratic itself has not changed. Only the window you are looking through has changed. Now let us see how to move between these forms with a single example. Start with f of x equals x squared minus 2x minus 3 in standard form. To get factored form, factor by finding two numbers that multiply to negative 3 and add to negative 2. Those are negative 3 and positive 1, so factored form is x minus 3 times x plus 1. To get vertex form, complete the square. Half of negative 2 is negative 1. Square that to get 1. Add and subtract 1 inside. X squared minus 2x plus 1 minus 1 minus 3 equals the quantity x minus 1 squared minus 4. That is vertex form. The vertex is at 1, negative 4. One function, three views, three different facts made visible. The leading coefficient a has two completely separate jobs. Its sign controls opening direction. Its magnitude controls width. Sign first. If a is greater than 0, the parabola opens upward and the vertex is a minimum. If a is less than 0, it opens downward and the vertex is a maximum. That is it for direction. Magnitude second. If the absolute value of a is greater than 1, the parabola is narrower than the reference y equals x squared, because the output grows faster for each step. If the absolute value of a is less than 1, it is wider, because the output grows more slowly. The reference y equals x squared has absolute value of a equal to 1. Do not mix these up. A common error is using the absolute value of a to decide direction, or using the sign to decide width. Every parabola has an axis of symmetry, a vertical line that acts as a mirror. For vertex form, a times the quantity x minus h squared plus k, the axis of symmetry is the vertical line x equals h. It passes right through the vertex. This means every point on the parabola has a mirror image at the same height on the other side of x equals h. If you know the vertex and one additional point, you automatically know its mirror point too. This mirror property is what makes the vertex so powerful. It is the exact center of the curve, and everything is symmetric around it. Let us put everything together and sketch a parabola from vertex form. The two key steps are, first, plot the vertex, and second, use the leading coefficient a to determine the shape. For example, take f of x equals 2 times the quantity x minus 1 squared minus 3. The vertex is at 1, negative 3, so plot that point. Since a equals 2, which is positive, the parabola opens upward. Since the absolute value of a is 2, which is greater than 1, the parabola is narrower than y equals x squared. You now know the turning point and the general shape before computing any other points. Now find the y-intercept and x-intercepts to complete the sketch. For the y-intercept, substitute x equals 0. F of 0 equals 2 times 0 minus 1 squared minus 3, which equals 2 times 1 minus 3, which equals negative 1. So the y-intercept is at 0, negative 1. For the x-intercepts, set f of x equal to 0 and solve. 2 times the quantity x minus 1 squared equals 3. Divide by 2 and take the square root. X minus 1 equals plus or minus the square root of 3 over 2. So x equals 1 plus or minus the square root of 1.5. That gives two x-intercepts, one on each side of the axis of symmetry. Now connect the dots with a smooth curve. Two methods to find the vertex. Method 1 is the vertex formula. X equals negative b over 2a gives the x-coordinate. Then you plug back into the function for the y-coordinate. Method 2 is completing the square, which converts standard form into vertex form, a times the quantity x minus h squared plus k, and lets you read h, k directly. Pick by what you need next. If you only want the numbers, the formula is faster. If you need the function rewritten in vertex form, for graphing transformations, for reading off the maximum value algebraically, or for symbolic manipulation, complete the square. Both methods give the same vertex. Method 1. The x-coordinate of the vertex is x equals negative b over 2a. To get the y-coordinate, plug that x back into f. Worked example. For f of x equals 2x squared minus 8x plus 7, identify a equals 2 and b equals negative 8. Compute x equals negative 8 over 2 times 2, which is 8 over 4, which equals 2. Substitute back. F of 2 equals 2 times 4 minus 8 times 2 plus 7, which is 8 minus 16 plus 7, which equals negative 1. The vertex is at 2, -1. The formula falls out of completing the square. The negative b over 2a term is exactly what makes the perfect square work. We will see why explicitly in Lesson 11 when we derive the quadratic formula. Method 2. Completing the square. To convert standard form to vertex form, we complete the square. Start with f of x equals x squared minus 6x plus 2. Take half the x coefficient. Negative 6 over 2 is negative 3. Square it to get 9. Add and subtract 9 inside the expression. X squared minus 6x plus 9 minus 9 plus 2. The first three terms form a perfect square. Factor to get x minus 3 quantity squared minus 7. Now we can read off the vertex directly. H equals 3, k equals negative 7. The vertex is at 3, negative 7. The non-monic case, where the leading coefficient is not 1, requires an extra step. Factor it out first, then complete the square inside the parentheses. Now let us connect quadratics to machine learning. You might wonder why we spend so much time on parabolas in a math course that leads into data science. The answer is that parabolas show up in two of the most important places in machine learning: mean squared error loss and the Gaussian density function. Let us look at each one. Now let us handle the non-monic case, where the leading coefficient is not 1. Take 2x squared minus 12x plus 7. Step 1. Factor the 2 out of the first two terms. 2 times the quantity x squared minus 6x plus 7. Notice the 7 stays outside. Step 2. Complete the square inside the parentheses. Half of negative 6 is negative 3. Squared gives 9. Add and subtract 9 inside. 2 times the quantity x squared minus 6x plus 9 minus 9 plus 7. Factor the perfect square and distribute. 2 times x minus 3, quantity squared, minus 18 plus 7. That simplifies to 2 times x minus 3, quantity squared, minus 11. The vertex is at 3, negative 11. Notice the 2 in front stretches the parabola vertically, but does not move the vertex. Two big machine learning connections. First, mean squared error. When you fit a line to data, the loss function, j of theta, equals the average of squared residuals. If you plot j against the slope parameter theta, you get an upward opening parabola. The vertex of that parabola is the optimal theta, the least squares solution. Second, the Gaussian density. The bell curve formula has an exponent that is a negative quadratic in x. Completing the square on that exponent reveals the mean, mu, and standard deviation, sigma. So the algebra we just practiced, completing the square, is exactly the tool used to read the parameters of a normal distribution from its formula. Let us look more closely at mean squared error. Imagine you have 3 data points and you are fitting a line with slope theta. For each value of theta, you compute the sum of squared errors, then divide by the number of points. If you plot that loss against theta, you get a parabola. The vertex of that parabola is where the loss is smallest, and that is your best fit slope. This is why gradient descent works so well for mean squared error. The loss surface is a smooth, bowl-shaped parabola with exactly one minimum. No flat regions, no local traps. Time for our practice quiz. 10 questions covering all the topics from today. Take a moment on each question before moving to the answer slide. Before we start the quiz, here are the 3 most common mistake families to watch out for. First, sign errors. When you read vertex form, a times the quantity x minus h squared plus k, the vertex is at hk, not negative hk. The sign inside the parentheses is already flipped. Second, arithmetic slips in completing the square. The most common one is forgetting to subtract the number you added, or when a leading coefficient is not 1, forgetting to distribute it back through. Third, form confusion. The y-intercept is c in standard form, not the vertex, and factored form gives you x-intercepts, not the vertex. Match the right form to the right question. Question 1. Which of these is the vertex form of a quadratic? Look at all 4 options and pick the one that matches the pattern a times the quantity x minus h squared plus k. The answer is C, a times the quantity x minus h squared plus k. Option A is standard form, option B is factored form, and option D is point-slope form for a line, not a quadratic at all. Vertex form always has a squared binomial plus a constant. Question 2. Find the vertex of f of x equals x minus 3 quantity squared plus 5. Look at the form carefully before answering. The answer is 3, 5. The function is already in vertex form. X minus h means h equals 3, and the plus 5 means k equals 5. A common mistake is to say negative 3, 5, but remember the formula has x minus h. Since we see x minus 3, h is positive 3. Question 3. If a is greater than 0 and f of x equals ax squared plus bx plus c, which direction does the parabola open? The answer is upward. When a is positive, the parabola opens upward like a bowl. When a is negative, it opens downward. The sign of a controls direction, while the absolute value of a controls width. Question 4. Complete the square for x squared minus 6x plus 5. Rewrite it in vertex form. The answer is x minus 3 quantity squared minus 4. Take half the x coefficient. Half of negative 6 is negative 3. Square it to get 9. Add and subtract 9. X squared minus 6x plus 9 minus 9 plus 5. Factor the perfect square. X minus 3 quantity squared minus 4. The vertex is at 3, negative 4. Question 5. Convert x squared plus 4x plus 1 to vertex form. The answer is x plus 2 quantity squared minus 3. Half of 4 is 2. Squared gives 4. X squared plus 4x plus 4 minus 4 plus 1. That factors to x plus 2 quantity squared minus 3. Remember, the vertex is at negative 2, negative 3. The h value is negative 2 because vertex form has x minus h, and we see x plus 2, which means x minus negative 2. Question 6. Find the x-coordinate of the vertex of 2x squared minus 8x plus 7. The answer is x equals 2. Use the vertex formula. X equals negative b over 2a. Here a is 2 and b is negative 8. So x equals negative negative 8 over 2 times 2, which is 8 over 4, equals 2. You do not need to complete the square for this one. The formula is faster when you only need the x-coordinate. Question 7. The mean squared error loss, j, of theta is a parabola in which variable? Look at the 4 options. The answer is theta. When computing mean squared error, the data points x and y are fixed. The loss function varies with theta, the model parameter you are trying to optimize. If you plot j against theta, you get an upward opening parabola whose vertex is the optimal theta. Question 8. Why is completing the square used in probability when working with the Gaussian density? The answer is B, to read the mean mu and standard deviation sigma from a Gaussian exponent. The Gaussian density has an exponent that is a quadratic in x. Completing the square rewrites that quadratic in vertex form, which directly reveals mu and sigma. This is the same algebra we practiced, just applied in a statistics context. Question 9. What is the vertex of f of x equals -2 times the quantity x minus 1 squared plus 3? The answer is 1, 3. Reading directly from vertex form, a equals -2, h equals 1, k equals 3. The vertex is at hk, which is 1, 3. Since a is -2, the parabola opens downward, making this vertex a maximum. The -2 affects direction and width, not the vertex location. Question 10. Why is mean squared error preferred over mean absolute error in many machine learning applications? Mean squared error gives a smooth parabolic loss with one minimum. This matters because mean squared error is differentiable everywhere, which means gradient descent works smoothly. It produces a convex parabolic loss surface with a unique minimum. Mean absolute error has a V-shape from the absolute value function, which is not differentiable at the minimum. This is why quadratics and parabolas are so central to optimization in machine learning. Let us recap Week 10. You learned 4 key outcomes. First, identify and convert between 3 forms of a quadratic. Standard form for the y-intercept, factored form for roots, vertex form for the vertex. Second, read a parabola's direction and width from the leading coefficient a. Positive a opens up, negative a opens down. Larger absolute value of a means narrower, smaller absolute value means wider. Third, find the vertex using either the formula x equals -b over 2a or completing the square. Fourth, connect parabolas to mean squared error loss in linear regression and to the Gaussian density function in probability. Watch out for the 3 trap families: sign errors when reading h from vertex form, arithmetic slips in completing the square, especially with non-monic quadratics, and form confusion, mixing up what each form tells you. Coming up next, Week 11, Solving Quadratic Equations. We will cover the zero product property, the quadratic formula, and the discriminant. We will also look at applications in projectile motion and optimization. See you there. That wraps up Week 10. Thanks for studying with us. See you in Week 11.